Welcome to lecture 22 of financial risk management, and this lecture is regarding option pricing model, and specifically we are going to discuss the Black-Scholes model that is used to determine the intrinsic value or price of the option. So what we are going to do is we are going to look at the Black-Scholes model for call option. And before that, if you remember, we started our discussion on option strategies, and based on those option strategies, we devised a model which was called put-call parity model, right? By Hans Stahl, and that model was used to find the premium, the call premium and the put premium. So intrinsic value of the price of the option. So when we say intrinsic price of the option, that doesn't mean the strike price, but rather it means the price of the option, which is the premium that should be paid. So similar to the previous lectures, let's say if we determine that the intrinsic option of a price of the call option is $1, and in market that option is being sold for $2, then we know that in market it is overvalued. That option is being sold at higher than the intrinsic value. So we shouldn't buy that option, right? Okay, so but then we determined that there are certain factors that would affect the value of the call or put option, and hence its price. When the value would increase, the price would increase. When the value would decrease, its price would decrease. Or I should say, when the value would increase, its premium would increase. When the value of the option would decrease, its premium should decrease. So, but those factors were missing in the put-call parity model. So we discussed in previous lectures that those models, those factors are covered in the Black-Scholes model, and so we saw the formula of finding the intrinsic value using Black-Scholes model for call option. That is what we are going to further explore in this lecture, and we are going to solve an exercise on this one. And then we are going to look at a Black-Scholes model for put option. So there are different, so we have a different equation for call option and put option of Black-Scholes model. So starting with the Black-Scholes model, we have seen this model in previous slide, in previous lecture. And the premium of call option is equal to S, which stands for spot price, into ND1. We will determine this ND1. Minus the exercise price into E is constant, which is 2.71 raised to power minus risk-free rate into time expiration, or it is similar to this portion can also be written as E divided by it would be E divided by ERT, right? Into ND2. D1 would be determined using this formula. It is natural log of spot price divided by exercise price plus the risk-free rate plus the variance. Remember, sigma square is used for variance, whereas simply sigma, just the sigma sign, is used for standard deviation. So in this formula there is a sigma square, which stands for variance, divided by 2, this whole multiplied by the time period, whole divided by under root of sigma square into t. When we determine the D1, we would use D1 to find out the value of D2. So D1 minus the under root of sigma square into t. This would give us a D2. So once we have D1 and D2, we would use these values to find their table values, tabulated values, and then those tabulated values would be used in this formula. So what I mean to say is that these equations would give us D1 and D2, but in the call option price formula, in the Black-Scholes formula for call option, we need to use ND1. So what we are going to do is, when we take the tabulated value of D1, that would be ND1, right? So this ND1 is nothing but the tabulated value of D1, and ND2 is nothing but the tabulated value of D2. Okay, so this is just the description that we have already discussed. S stands for current stock price, E for exercise price, R for risk-free rate, and remember, this risk-free rate should be continuously compounded. If it isn't, then you need to convert it into continuously compounded using the formula that we have discussed in our previous chapter. But in the examples that we discuss in these videos, we would simplify them, right? The continuous rate would already be given. Sigma square is variance that I have already discussed. Then T is time to expiration, and ND1 is the probability that a standard deviation or normal distribution variable will be less than. In simple word, it is the table value. So starting with the example, if S is 95, so the spot price, the current market price is $95 of a stock or a asset. Its exercise price is 100, so we have determined that at the end of expiration, this stock or this asset would be traded at $100 no matter what the price in the market is. The time period is 3 months. So the contract would expire in 3 months. So if we divide it by 12, we would get 0.25, right? So in formula, it would the T would be equal to number of months divided by 12. Then we have sigma square, which is variance. It is 0.04. The risk-free rate is 0.10 or 10%. So let's solve it. So first we need to find a D1, right? The formula for D1 is a natural log of S divided by E. S is spot price and E is future spot price. Sorry, it is strike price, plus the interest rate, plus sigma square divided by 2, this whole multiplied by T, the time period, which is 0.25 in this case, this whole multiplied by under root of sigma square into T. If we plug the values, then our spot price was 95 in previous example, exercise price was 100, the risk-free rate was 10%, if you remember, that is 0.10. Sigma square was 0.40, this would always be divided by 2. T was 3 months, so 3 by 12 would be 0.25. So whole divided by 0.04 into 0.25. Now somewhere you might see this as being written sigma under root T. The both terms are same, but what essentially it has done is that the square and the under root would cancel out. So this would be written as this. So just in case, if you look at the formula in your textbook, you might see this term. So you don't need to get confused here. Okay, so let's simplify this. It would give us the value of D1 as minus 0.21. So we cannot interpret this D1 value, right? For now, the value is minus 0.21, and we would further look at into this. D2 is equal to D1 minus under root sigma square T. So D1 was minus 0.21 minus under root 0.04 into 0.25, time period was 3 months, 3 by 12. So if we simplify this, we get the D2 value of minus 0.31. So for now, we have just calculated the D1 and D2. We do not have the value of ND1 and ND2. We first need to find the value of ND1 and ND2. Now, how do we find ND1 and ND2? We look at the tabulated value of D1, that would become ND1, and we look at the tabulated value of D2, that would become ND2. Okay, so let me show you how to find the tabulated value. Just remember that our value is minus 0.21 and 0.31. Let's ignore the minus sign and we would come back to the minus sign later on. So 0.21 and 0.31. So let's go towards the table. This is just an excerpt from the table. The whole table is in the shared folder in option pricing, within the option pricing subfolder. So D1 was 0.21. So we would look at the leftmost value over here. This would be 0.2, right? This part had been done. We are left with 0.01. This is 0.01. So we get at the intersection of these two, the column and the row, we get 0.832. So our D1 is 0.5832. What about, this is ND1, right? Let's not call it ND1, I will get back to this one. So the tabulated value is this one. What about D2? D2 was 0.31. We look at the 0.3 on the rows and 0.01 in columns. We get the value at the intersection of row and column. We get the value of 0.6217. This is our D2. So let's get back to the previous slide. So we need to find ND1 and ND2. The table value of D1 is 0.5832. We have just seen how do we find the tabulated value. We have found the tabulated value. We have found the tabulated value of D2, which is 0.6217. Now, here is some differentiation. We need to find ND1 and ND2. If D1 is positive value, then the tabulated value would be ND1. Similarly, if D2 is a positive value, then the tabulated value of D2 would be ND2. This is what I have written. If D1 is positive, then ND1 is equal to the table value of D1. So if D1 had been positive, then this would have been ND1. But in our case, D1 was negative. If you remember, it was minus 0.21. For that, if ND1 is negative, if D1 is negative, then ND1 is equal to 1 minus the table value of D1. So it would be 1 minus the table value. So in case of D1 and D2, they both were negative. So in case of negative value, to find ND1, we would have to use this equation. So ND1 would be equal to 1 minus the table value of D1, which would be this value, and ND2 is equal to 1 minus the table value of D2. It would be this value. So once we have these values, we are going to input these values into the call option formula, and that formula is this one. So spot price into ND1. ND1 is 0.4168, spot price is 95, minus exercise price is 100, into E raised to power minus 0.10, 10% rate of risk-free rate, into 0.25, which is time period, into ND2, and ND2 we found it in our previous slide. So if we simplify this, we get the C value of 2.806. Now this is what we need to interpret. What this means is that based on the Black-Scholes formula, remember, instead of put call parity to find the premium of call option, we are using the Black-Scholes model. The intrinsic value of premium of call option is $2.80. This means that if, let's say, in market, this call option, this particular call option of the same expiration, same risk-free rate, same quantity, same asset is being traded at, say, $4. If the premium in the market is $4, then we would say that in market this call option is overvalued, right? Because we find that the intrinsic value should be 2.80 and in market it is being traded at $4, so the call option is overvalued. If instead, so we wouldn't buy this call option. If instead in market it was being traded at $1, then we would say that in market it is undervalued. It should be traded at 2.80, but rather it is being traded at $1. So we should buy it because it's being sold at a lesser price. Okay, so we have found the intrinsic value of the call option, but now we need to find the intrinsic value of the put option. Now, in real world, it would depend on whether you are going to trade a call option or put option. So if you are going to trade a call option, then this is what you need to find, right? You are done with your task. But if you needed to trade a put option, then you would have to do one further step. And that further step would be to use the same Black-Scholes formula to find the price of the put option. And this would be price of put option or premium of put option, the intrinsic premium of the put option or the intrinsic price of the put option is equal to the price of call option that we just found in previous slide. This one, 2.806 plus E, which is exercise price, divided by ERT. Remember, this can also be written as E into E raised to power minus RT. So in previous example, I wrote it in this way, just to give you an idea. Minus the spot price. So P stands for price of put option, C stands for value of call option, E stands for exercise price, S naught stands for current market price of the underlying stock. So let's solve this. We put the value of 2.806 that we got from the call option premium formula plus standard exercise price divided by E raised to power the risk-free rate and the time duration minus the spot rate. If we simplify this, we get the value of P is equal to 5.33. So this for this specific asset, the option where the underlying asset is, say, something, the put option's intrinsic value is 5.33. So if this option is being sold in the market at 10 rupees, then this option is overvalued in the market. If it is being sold for 2 rupees, then it is undervalued in the market. So in this case, we wouldn't buy it from the market. If in this case, we would rather prefer to buy it from the market. So the idea is that put call parity formula or the equation or the model did give us the price of call and put option, but it had some shortcomings. So there was another model that was developed by the name of Black-Scholes model, and it would always also give us the intrinsic value of put on or call option.